Hey there, AP Calc friends. So let's talk about these volumes of revolution. So we just learned about disks and washers, and we realized that washers are probably just the way to go for all these kinds of problems. But now when we spin around a different axis, it gets hard. So what I have for you are some really helpful formulas that if you can just plug these in, you'll be good to go, and you don't have to worry about visualizing exactly what these radiuses are going to look like. But still, we're playing with washer formulas. So again, that's going to be the big R, or the outer function squared, minus the inner function squared, times pi, which we can bring outside. dx if we're spinning vertically and we have vertical slices, and dy if we're doing horizontal slices. All right. Well, let's speak about the vertical revolutions. If we're spinning it vertically, like around the x-axis, or around something like that, where it's a y equals horizontal line. When you spin around a horizontal line, you make a vertical revolution, which means your slices are now along the x-axis, so there'll be a width of x, or dx. So when you see a vertical revolution, you think two things. First of all, you're spinning around some y equals k horizontal line, and you're going to be using dx, which means everything should be solved for y equals for your formulas. All right, now which one do you put first? Is it the axis and then you subtract the function? Here's what I think. If your axis here, if k, your horizontal axis, is above or greater, again, when it's greater, I'm thinking the word above. So you have your functions below it, and your axis that you're going to spin it around is above both of those functions. We use this formula here. The volume is pi, the integral from a to b of, now you do it this way. You do k minus the outer function when you spin it around, squared, minus k minus the inner function, squared, dx. Okay? So it's still important that you look at the picture of the graphs and know which one will be your outer and which one will be your inner. That will be really important. All right, well, what if by chance the axis that you're spinning around, your k value, is actually below the other two functions? So the outer and inner functions, that area that you're going to spin around is actually above the horizontal line k, or k is below. If that happens, then these are what your big R and small r look like. So the outer radius would actually be the outer function minus the axis, and over here the small r would be the inner function minus the axis. Both squared and both subtracted. And again, because we're doing vertical slices here, it's dx. Now, here's a cool little shortcut to think about it. If you just remember one of these formulas, you're good to go. And the reason is, if by chance you mix them up, you'll know because you'll get a negative volume, which, as you know, is not possible in real life. You can't have a negative pi over 5 volume or whatever. So if you do it and you feel like you did it right, especially if you did calculator and you got a negative volume, well, that's okay. It just means you picked the wrong formula. So switch the two radiuses. Put them in different spots. And then go back and recalculate it, and you'll get a positive volume. So if you're not sure which of these two equations to use, is it the axis first or the function first, go ahead and try one of them. And if you get overall a negative answer, then you just got it wrong. You just got to flip it. But these are two great formulas if you're doing a vertical revolution around a horizontal line. Got those down? Okay, let's do the other way around. What if you're spinning around a vertical line, like an x equals h by chance? Now when you're spinning around horizontally around a vertical line, the slices are now along the y-axis, so it's going to be a dy. Again, same washer formula over here, but we'll be using dy, and we're spinning horizontally. So which one comes first, axis or functions? Well, same idea. If your axis is greater than, which means to the right, if your vertical line, the axis you're spinning around, is to the right of the functions, then you'll use this formula here of axis minus the outer squared minus axis minus the inner squared, dy. And also just know that these a's and b's are the y values because we're in dy land. And then what if by chance the h vertical line is actually to the left of the two functions? So the functions are actually greater than the axis. Then you'll use this direction. It's outer minus the axis and inner minus the axis in that order. But again, the same shortcut works. Now, by chance, if you have them mixed up and you get a negative volume, just switch the formula around. But if you can remember these 4 formulas, 2 for the vertical revolutions and 2 for the horizontal revolutions, you'll be good to go. All right, shall we try one? This is actually number 15 from our textbook. Let's try this one. So we're going to take this function here, straight line, this one here, parabola. Let's find that bounded region. And then what happens if I spin it around the horizontal line y equals 3? I make a 3-dimensional shape. I need to find the volume. All right, let's first try to graph these. If I just do it in terms of y equals x minus 1, that might be a little bit easier to see. So that's a slope of 1 and a y-intercept of negative 1. Okay, there's that one there. Now, to do this parabola over here, probably the best thing to do is try to figure out where the x-intercepts are. So let's solve for the zeros by factoring it. So I know the x-intercepts are at 1 and 3, which is here and here. That means my parabola probably looks something like this. Okay, so the way the parabola turned out, it is below the straight line, which is great. So that means our shaded region would be this region right here. Great, and now we're going to spin it around the line y equals 3. All right, so y equals 3 would be this line up here. So a couple things. This is a horizontal line, so that means we're spinning it vertically. It's going to be spinning around this axis here, which means my slices are going to be vertical, which means this is a dx. And notice that the axis here is greater than the functions. So we use the one where, as we saw before here in the first one, use this one right here, where if the axis that we're spinning around is greater than the functions, do axis minus the outer and axis minus the inner. All right, let's try it. So now, because we're doing dx, we're going to need everything in terms of y's equals x's, which is mostly done for us. That's great. Okay, let's just start setting it up. So the volume will be pi first, because we put that on the outside. The integral from where to where? Now that I don't know yet. Why don't we come back to that in a second? But let's try to do big R squared minus small r squared. And here it's going to be the k value minus the outer and the k value minus the inner. All right, well the k value is 3. That's not too bad. But now we have to use a little bit of visualization. When we spin this region vertically around the y equals 3 line, can you see which one is going to be on the outside? What's the outside of that ball or that shape or whatever you want to call it? If you see when you spin it around, this here, the parabola, will be your outer. And therefore, the inner will be the straight line. Okay? So if I do that, that means my outer will be 3 minus, parentheses, my parabola. That's the entire big R, square it, minus axis, minus, and the inner was the green, so that's going to be the line x minus 1. Whole quantity squared, close it up, dx. All right? So that's basically what this integral is going to look like. But we do need the limits. So let's figure out, I'm going from here to here on my shaded region. We need to find that out. So just like old time's sake, let's set these two equations equal to each other and find the intersection points. I'll do that down here. Where does x minus 1 equal the parabola? And if I just move some furniture around, I can factor that pretty easily. And I get x minus 4, x minus 1. So therefore, my intersection points, both the line and the parabola, are going to meet at x equals 1 and x equals 4. And just to confirm, again, just use a little common sense. Does that make sense on our picture up here? Let's see. Yeah, right here it definitely looks like 1, because that was going to be the x-intercept of the parabola, as we saw over here. And then if the other x-intercept was 3, right over here, from this, that makes sense that over here is about 4. Great, so 1 and 4 works, so I'll put that on my integral limit. It's going to be going from 1 to 4. Great, now we could do this by hand by maybe distributing that negative in there and then foiling. And over here, distribute the negative and foiling. It's going to be a lot of just brute work. But for some of these for now, if you just want to use the calculator to plug it in, that's probably the best. If you want to try it, this one turns out to be 108 over 5 pi is my final answer. Doing it by hand is fine. It just takes a long time. There's some big numbers there. But if you want to try this with a calc. But the most important thing, especially on the AP, is can you write the integral out? Sometimes that's all they want to see. They don't want the final answer. They just want to see what the actual integral looks like. So using our cool, nifty little formula, does that make sense? So that's how we're going to do volumes of revolution when it's around an axis that's not our normal x and y axis. Hopefully these formulas are going to help you out greatly, and we'll practice some more next time. See you then.